Hello and welcome to lecture 42 of the course Computational Complexity. In the previous lecture, we started on showing the proof that parity is not in AC0, right? And we were following the proof technique by Rasberov and Smolinsky. And the main motivation was to provide concrete, meaning unconditional lower bounds on some circuit class, right? And I'll just very briefly outline what we have done so far on the proof itself, right? So what we have done so far, this is the high level outline of the proof. That every AC0 function can be approximated by a low degree polynomial over the F3 field. F3 field is just the field which contains 0, 1 and 2, and addition and multiplication happens modulo 3, okay? So that is F3. So every AC0 function can be approximated by a low degree polynomial, right? And second, parity cannot be, parity requires a large degree even to approximate, right? These are the two main theorems that we will show. And in fact, we showed the first statement and a bit more than that, right? So the first statement was showed that every AC0 function can be approximated by a low degree polynomial. So by low degree, what we meant is if it is a circuit of size S and depth D, then we could approximate with a log S to the power D degree polynomial, and the error of that is like 1 by 4, okay? So let's say 1 by 4 is some fixed number, so it could be 1 by 10 also, then still some constant factor will change, but we will get roughly this. So log S is where S is the size of the circuit, so it is like log n to the power d, because S is just n to the power some k. The main idea was to build a circuit where we replace AND gate, OR gate and NOT gate with the corresponding polynomials. And what we did in this proof is to show that we could approximate OR gates. NOT gates are straightforward because it is just corresponding to the polynomial 1 minus x, and AND gate can be derived from OR gate using the De Morgan's laws without any extra degree. So all we had to do was to build an OR gate, which we did, and we built an OR gate that had degree order log 1 by epsilon, where epsilon was the desired error. Now we just use these OR gates, AND gates, everything, NOT gates to replace, so the polynomial corresponding to the OR gates, NOT gates and AND gates to in the circuit to build a jumbo polynomial that would approximate the original circuit. So the jumbo polynomial has like the error is approximated by the union bound, so we choose epsilon small enough so that epsilon times the size is also less than 1 by 4, and the degree will be the degree of any individual polynomial to the power the depth of the circuit, because it would be an iterated polynomial of a polynomial of a polynomial. So therefore, if you do the math, you will get that epsilon has to be 1 by 4s and the degree will be order log s whole power d, right? So this is not a single polynomial but a family of polynomials, rather a polynomial chosen from a distribution at some using some random bits, right? And which will, so and when I say epsilon here, the epsilon is over the choice of the randomness and for any fixed input. So even after you fix the input, the probability of success is at least 3/4. And then we showed that if we have a family and a distribution that epsilon approximates or 1 by 4 approximates, then there is a single polynomial, there is one polynomial in that in the distribution that will actually give us at most 1/4 error if you choose the input at random. Okay, so now from the situation where we want for any input at most 1/4 error over the where the error is computed or the probability is computed over the choice of the polynomial, you can move to a situation where polynomial is fixed, the error, the probability is over the choice of the input. This was a very simple argument using some counting based argument, right? So the main technique for the first part was this arithmetization, how to write the OR using some polynomial, right? So now we are starting off from here. Suppose there is a function that is computed by a size s and depth d circuit. Then there is a fixed polynomial, we'll call it qx. Okay, so this is fixed over f3 such that the degree is order log s power d, and the probability is chosen over the inputs. Then what is the probability that the q agrees with the function that we want to compute? And this is at least 3/4. Okay, so this 3/4 also choice is somewhat arbitrary. I could have made it 9/10 or something, right? It would still, you could get a similar proof. Okay, so this is where we are starting from. Maybe I have repeated in this notes as well, the second notes as well, the 42 notes. So if we have a Boolean function computed by depth d and size s circuit, then you could have there is a fixed polynomial that has degree log s power d and not even approximates it, such that the polynomial agrees with the function on 75% of the inputs. Okay. So this is what we will see today, and sorry, this is what we already saw, right? What we will see in this lecture is that for any fixed polynomial that for which agrees with the parity function on 75% of the inputs, this polynomial should have degree at least square root n divided by 10. Okay, so any fixed polynomial that agrees with parity function, right? Recall that parity of x being a bit string, is 1 if and only if an odd number of ones in x are 1, or if x contains an odd number of ones. If x contains an even number of ones, parity is 0, right? It's just the bitwise, like, or it is just the XOR computed over the bits. So what we are saying is that if qx or if parity is computed by computed by a polynomial in this manner, like such that the polynomial agrees with parity on 75% of the inputs, then the degree of the polynomial should be at least square root n divided by 10. And what we are saying here is that for any function that is computed by a size s and depth d circuit, then if it agrees with any polynomial that agrees with it, or there is a polynomial that agrees with it on with degree at most log s power d. So when it is an AC0 circuit, it's like this log s power d is order log n power some constant. Sorry, log n power some constant, right? Because order log s is just k times log n for some constant. Depth d is a constant, right? So this is, so log n power d is much smaller than square root n. Here we are, the second theorem, we are saying that any polynomial that approximates parity in this manner requires square root n degree. Here we are saying log n power constant is enough. So that is the contradiction. So because of that, we cannot compute the parity using an AC0 circuit. This is a contradiction. In fact, we will see a bit more detailed than this. So we will see, so we will actually compute how much size can the parity circuit have if it has constant depth, and we will see that the size is more than polynomial. Okay. Okay. So yeah, so this is what we said. Okay, so yeah, so this is what I just said. If you combine the above theorems, right, what it's saying is that if parity has to be approximated by polynomial in this manner, degree has to be at least square root n divided by 10, which means order log s to the power d has to be square root n divided by 10, which means s has to be square root 2 power square root n divided by 10 whole power, or power 1 by d, which you can just write it as 2 power n power 1 by 2d, right? So any circuit that computes parity, so any circuit any circuit that computes parity must have size at least this quantity, right? That is the, so which is, this is clearly super polynomial. This is like this is like something exponential. That is the reason why parity is not in AC0. So now what remains is to show the proof of this theorem. Okay, that any Q that agrees with parity on 75% of the inputs must have square root and degree, square root and divided by 10 degree. Okay, so we'll shoot for a contradiction. Again, this proof is also very simple, but very simple and uses simple principles, but this uses a bit of linear algebra and it will be shorter than what we saw in the previous lecture. Okay, suppose there was such a Q with degree less than square root and divided by 10. Okay, first let us do a change of basis. Okay, let us do a change of basis. So let us define Q prime. And what is Q prime? It is 1 minus 2Q of this. So where we are replacing the variables. So the variables of Q are x1, x2, etc. So now we are replacing it with 1 minus x1 divided by 2, 1 minus x2 divided by 2, and so on, up to 1 minus xn divided by 2. So what have we done here? When xi is 0 or xi is 1, I'm sorry, Q computes parity on Boolean inputs, right? Q computes parity, maybe I'll write over here, Q computes parity on Boolean inputs, right? This is what it computes, 0, 1 power n. Now the claim is that Q prime computes parity on minus 1 plus 1, or rather maybe I should say the opposite. Just to be consistent, plus 1 minus 1 power n plus 1 minus 1. Okay, so suppose xi, so suppose the input of Q, or sorry, Q prime is actually, so Q prime takes as input x1 up to xn, right? And think of x1 etc. Coming from plus minus 1, not 0, 1. Now what is happening here is that if x1 is 1, then 1 minus x1 is 0. So 1 minus 1 divided by 2 is also 0, right? However, if x1 is minus 1, then 1 minus minus 1 is actually 2, and 2 divided by 2 is actually 1. So when xi is 1, it gets maps to 0. When xi is minus 1, it gets mapped to 1. Okay, and Q computes the parity over the Boolean inputs, right? So it says it says whether, it checks whether an odd number of ones are there or an even number of ones are there. So if there is an odd number of ones, it outputs 1. If it outputs 1, then we get 1 minus 2 in the right hand side, which is 1 minus 2 is actually minus 1. If it outputs 0, we get 1, right? So you can check that Q prime computes parity over plus minus 1 inputs and outputs minus 1 if and only if an odd number of my inputs are minus 1. Okay, so it is exactly like 0, 1, but it is like we replace 0 with plus 1 and 1 with minus 1. So this helps because now we'll see why it helps. Right? We'll see why it helps. We can now write a simple polynomial for this, and that will help us in some aspects. Right? The fact is that Q prime simply does a change of basis from Q, going from 0, 1 to plus minus 1. Right? And it does so without any change of degree. It is just linear operations here, 1 minus 2Q. Okay, so degree of Q prime is the same as degree of Q. Okay. So since Q computes parity, or Q is supposed to compute parity on at least 75% of the inputs, Q prime also computes parity on the same 75% of the inputs, but Q prime has this change of basis. Okay. So that's where we are now. So yeah, and in this plus minus 1 basis, right? What is parity? Parity is just the product. So what is the product of xi's, where the xi's come from plus minus 1. So it will be just how many minus 1s are there. If there is an odd number of minus 1, the product will be minus 1. If there is an even number of minus 1, the product will be plus 1, which is exactly what parity has been defined to be. Right. So we can replace parity with this term over here, or this term over here, right? Product of all the individual xi's. So what is the probability that q prime x is equal to this? Right. This is the same as parity. It is at least 3/4. This means that there is a set A, right? It agrees with the parity on 3/4 many inputs. So let those inputs on which q prime agrees with parity be called the set A. Okay. So in other words, maybe I can write here. In other words, A is the set of all x plus minus 1 power n, such that q prime x is equal to the product of xi. Right. And we know that A agrees with parity, or the q prime agrees with parity on 75% of the inputs. So A is of size at least A is of size at least 75% of the entire domain. So the domain is plus minus 1 power n, which is of size 2 power n. 75% is 3/4 of 2 power n. On this many inputs, q prime agrees with parity. Okay. Now we will see an interesting claim that if now consider any polynomial, okay, any polynomial h, or any function g, sorry, consider any function g, okay, over f3. For any g, it doesn't matter what it is. Now we can write a polynomial h, okay, that has the following properties. When restricted to A, h is equal to g. Okay, so A is this set where q prime is the same as parity. So under that set, this polynomial and this function will be the same. Okay, under that set, the polynomial will equal the function, and then the degree of h will be degree of q. Okay, whatever it is. So by assumption, degree of q was less than square root n divided by 10. Right, this is what we assumed. Okay, degree of h is degree of q plus n divided by 2. So degree of q, in fact we can go on and write that degree of q is actually assumed to be square root n by 10 plus n by 2. We have, by assumption, we already have this. Right. So whatever be the function, now we are saying that if there is such a polynomial, whatever be the function, just because parity can be approximated, that implies that any function can be approximated by a polynomial of degree very close to n by 2. And that seems unbelievable, and that is what will give us a contradiction, right? So it's saying that any function that you take, as long as you're only looking at this set A, so recall that A is 75% of the inputs. If you're restricting yourself to this set A, then you can approximate it with a polynomial of degree roughly n by 2 plus something like square root n. So square root n is much smaller than n, right? So the point is that there are too many functions g, right? G could be any function, and if we restrict ourselves to low degree polynomials, or polynomials of degree n by 2, there are not enough polynomials. So the number of functions and number of polynomials will be, there is a huge difference, and that will give us a contradiction. Okay, so now first let's prove the claim why this is true. So this claim is true as assuming whatever we have so far. So we assume that q is of degree, the parity approximation polynomial q is of degree at least, at most square root and divided by 10, and that gave us this particular q prime, right, and that will give us this claim. So we have a function g, and we will see how to approximate, how to get a polynomial h that approximates g. Okay. Okay, so g, so first of all, g has a polynomial, right? So g is a function. So g, you can write down the entire polynomial in f. First thing, an entire polynomial over f3, right? So there will be a huge polynomial. First thing to notice that g is over. So we are only bothered about the elements in A. So A is a subset of plus minus 1 whole power n, right? Okay. So inside this, if there is any xi squared or xi squared, we can replace it with 1, right? Because all xi's are plus minus 1. So xi squared is always 1. So any term, like if you see xi power 10, you can make it 1. Xi power 11, xi power 10 is 1, so xi power 11 is just xi, right? So all that will remain is, all the terms will be either degree 1 or 0. So it will be a multilinear polynomial, right? So this will give us multilinear polynomial. Sorry, right? So you start with the polynomial for g. Now we are simplifying it, right? So multilinear polynomial is it's still fine, right? As long as we are restricting ourselves to a, and that's all that we care about, right? And now you look at each monomial. So each monomial will be of the form xi, a product of xi where I comes from some set S, where S is some subset of 1 to n, right? Now if this set is of size smaller than n by 2, then we just retain the term, right? Because again, the target degree that we have is something like n by 2 plus some small thing. So if this s is smaller than n by 2, we are fine. The degree will be smaller than n by 2. If it is bigger than n by 2, then we have to do something. So all that we need to notice is that if s is bigger than n by 2, you could write it as the product of all the I multiplied by the product of I that are not in S. Okay, so product of all the I, which is the second term here, multiplied by the product of I that are not in S. Because the I that are not in S appear twice, and xi squared, as I said already, is equal to 1. So all that will remain is all the I that are in S. Okay, but what is the product of all the I, all the xi? It is simply inside A, it is simply q prime x, right? This is the assumption. Within A, q prime and this are same, right? So this is the same within A, and we only care about what is there within A. So we get this, and since S is in this part, S is assumed to be of size bigger than n by 2, the complement of S will be always less than n by 2 or at most n by 2, right? So this is degree, this is degree less than n by 2, and this is degree less than square root n by 10, right? So and we get such a polynomial, right? So we got a polynomial of degree n by 2 plus square root n by 10. Now where is the contradiction? The contradiction is, so again the claim is now proved, or this particular claim is now proved. Now we will get a contradiction. Let's see, just 1 second. Okay, what is the contradiction? as I already said, how many functions are there? Consider all the functions that go from A to F3. Okay, how many functions are there that go from A to F3, right? So the number of functions is actually 3 power A. These because each entry in A could be 0, 1 or 2, right? Each entry in A could be mapped to 0, 1 or 2. So there is a set A which has 2 power n elements, and then F3 which has 0, 1 or 2, right? So each one of them could be mapped to one of these. Each one in the left hand side could be mapped to 0 or 1 or 2. So it's 3 power 2 power, or sorry, 3 power A, or 3 power 2 power, 3 power the size of A, right? And so now another thing that we know is that all these functions are approximated or captured by polynomials, not even approximated, actually captured by polynomials of degree at most square root n by 2, n by 2 plus square root n by 10. Now we will just count how many such polynomials are there, and we further know that these are all multilinear as well. So how many such monomials are there? So how many monomials can we form of this degree, right? And then you could add them and all that. So we'll see how that works. How many such monomials are there? So the degree is at most n by 2 plus square root n by 10. So it is just the number of ways to choose, right? So there is one is a constant term, and then so I'm not counting the coefficients now. So the constant term is this constant term. N choose 1 is the single degree terms. N choose 2 where you choose 2 xi and xj, and so on up to n choose n by 2 plus square root n by 10. So up to n choose n by 2, right, up to the halfway mark, we know that 1 to halfway mark, this is the middle binomial coefficient. So this is like at most half times 2 power n, right? So we know that all the binomial coefficients 1 to 1, n choose 1, n choose 2 up to n choose n will give us 2 power n as a sum. So up to the midway point, it will be at most, it will be equal to half times 2 power n, okay, up to the midway point. And then what remains is n choose n by 2 plus 1, n choose n by 2 plus 2, and so on up to n choose n by 2 plus square root n by 10. Okay. So this first part is done. This is simply half times 2 power n. Right. Second part, one has to notice that there are, how many terms are there? There are square root n by 2, square root n by 10 terms, right? This is the summation over here. And we know that the middle binomial coefficient is the largest. And what is the middle binomial coefficient? It is n choose n by 2. So each one of them can be upper bounded by the middle binomial coefficient times the number of terms here, which is square root n by 10. And middle binomial coefficient, you can actually use Stirling's approximation here. So this is what we have used here. This is Stirling's approximation, right here, which states that n factorial is, I have written below in the red, n factorial is n power n divided by e power n into square root 2 pi n. So n choose n by 2, if you write n and n by 2 factorials in this form, you will get this 2 power n divided by pi n divided by 2, and which is what I have replaced here. This is n choose n by 2. So you can cancel the square root n's, and what is left is 1 divided by 10 square root of pi by 2 multiplied by 2 power n. This is what we have. Okay. Now what is 1 divided by 10 square root of pi by 2? Anyway, so it is smaller than 1 by 10, right? So whatever square root of pi by 2 is, pi by 2 itself is 1.5, 1.57, and square root of that may be something, it's something between 1 and 2, let's say. So this is like less than 1 by 10, right? So this is smaller than 1 by 10. And the first term, so again I am starting from this point here. The first n by 2 terms were at least half times 2 power n, and then the remaining terms were 1 divided by 10 square root of pi by 2 power n, right? So, and I said this entire thing is less than 0.1, right? The second term. So overall we get that this is at most 0.6 times 2 power n. This is the number of different monomials. And how many ways can you, how many polynomials can we generate? So each monomial can get coefficient 0, 1 or 2, right? So it is just 3 power this, right? So number of polynomials is 3 power 0.6 times 2 power n. But I have already said that the number of functions from a to f3 is actually 3 power the size of a, right, which is 3 power 2 power n. So there you see the mismatch. Number of functions is actually 3 power the size of a, which is 3 power 2 power n. That gives the mixed mismatch. By whatever we have assumed so far, we got that the number of each function can be written by a polynomial, meaning each function, as long as we are restricting to ourselves to a, we can represent it by a polynomial. But then the number of polynomials is smaller than the number of functions, so that leads to a contradiction. Another way to see it is that all these functions form a vector space, and the dimension of this vector space must be of size a, the size of a, which is actually 2 power n. But sorry, not 2 power n. I'm sorry, even here I have to, this is like 0.75 times 2 power n. Over here also 0.75 times. I think here also I said it wrong. Right? So size of a is this, but here we are saying the number of monomials only 0.6 times 2 power n. So that's a contradiction. Right, so that's it. So we assume that parity could be written as a small degree polynomial, or small as in roughly n by 2 degree polynomial, and that gave us that there is a large set in which any function can be approximated by a roughly n by 2 degree polynomial. And sorry, I have to repeat. We assume that parity could be approximated by a square root n degree polynomial, and that gave us that there is a roughly large set of say 3/4 times 2 power n, and all the functions from that set can be approximated by a polynomial of degree roughly n by 2. But then that doesn't add up because number of functions is way more than the number of polynomials, right? And that gives us a contradiction. And yeah, that's about it. So we cannot have a degree square root n divided by 10 polynomial approximating or even computing parity. In fact, in the last lecture we saw that epsilon approximation or 1/4 approximation leads to a concrete polynomial that agrees with parity on 75% of the inputs, and that is not possible, and it completes the proof. Okay, I think I have gone over the details carefully, so I will not really go over again for a summary, but I will just like to add some points, right, some 2-3 points, right. In fact, this proof is actually more general, right. We can actually use it to show that parity is not in AC0 AC03, right. What is AC03? AC03 is the class of it is just like AC0, but in addition we also have mod 3 gates, right. So it is polynomial size, constant depth, and not gates of unbounded fan-in, but we are also allowed to use mod 3 gates. Okay, so what is mod 3 gates? So what did I define parity as? Parity is the if there are odd number of ones in the input, it outputs 1. If there are even number of ones in the input, it outputs 0. Just like that, if the number of ones in the input is a multiple of 3, this will output 0. If the number of ones in the input is not a multiple of 3, it will output 0. So it is like parity. What parity was for 2, mod 3 is for 3. And you can say mod 5 or any number, right? So in this case, AC03 is what I am saying. This proof also can be used to show that parity is not in AC03. So even if you allow the circuit to have mod 3 gates, still parity is not computable. Why is this? So the first half of the proof will work even in this case, right? So second half of the proof doesn't need any changing, right? The fact that parity requires a large degree doesn't need any changing. What has to be fixed, or what has to be modified slightly, is that computed by a circuit that we said here in the proof that we already saw. Even if that circuit has a mod 3 gate also, even then we have to approximate polynomial. So we saw how to approximate AND, OR and NOT, but even mod 3 has to be approximated. And it may not be that hard to convince yourself that you can also approximate mod 3, because we are already computing over F3, right? So we are already the computations over F3. So how do you compute mod 3? So F3 things happen already in mod 3, but now how do you compute mod 3 over F3? That you can think, right? So once that happens, then you can generalize this, or you can modify this theorem that we saw in the previous lecture to say that everything that is computed by a size S, depth D, a circuit of which has AND, OR, NOT and mod 3 gates can be approximated by a low degree polynomial, and the second part is the same. Okay, so this is one point. The proof is actually stronger than what we already saw. So maybe I'll just write here. So check mod 3 gates can be written as a small polynomial, as a low degree polynomial over F3. F3 once again is the field 0, 1, 2 that contains 0, 1, 2, and everything happens in modulo 3, right? In fact, it actually shows the same technique, exactly the same proof works. So parity is like mod 2 and AC03 is mod, like 3 contains mod 3, right? So now instead of mod 2 and mod 3, I could say the same for mod P and mod Q. So any mod P is not contained in AC0Q, where P and Q are two different primes, right? Maybe another thing that you can check is, okay, maybe I'll skip that. So maybe I'll just say it. Another thing that you can check is if we need P and Q to be two different primes, otherwise this doesn't work. So for instance, if you can always write mod 3 using, let's say, mod 9 gates, for instance, right? Just think about it, how you will do that, right? So if they are not primes, sometimes these kind of things happen. Now this is AC0Q. What if we allow, so one point is this, so we have a language parity that is not in AC0. Do we know a language that is not in AC0Q? Yes, I just said mod P is a language that is not in AC, or a function that is not in AC0Q. What if when Q is a prime, but we did not know any language, or we did not even know if there is a language or a function that is not in AC06, right? So 6 does not get captured in the previous statement over here, right? Because this statement mod P is not in AC0Q only held for P and Q primes, right? So we did not know of a language that is not there in AC, or even if was there a language that is not there in AC06. And so suppose we allow right? So is there, so parity and mod p are like small languages, and till about 10 years back we didn't know this, and Ryan Williams showed that there are languages. So in fact, so it's not in p, np, exponential time, nothing. So he had to go till nexp to find a, or to show that there is a language in nexp that is non-deterministic exponential time, that is the class nexp. um, there is a language in nexp that is not computable by AC06. AC06 means AC0 circuit along with mod 6 gates. In fact, he proved slightly stronger statement. He said that there is a language, there are languages in nexp that is not in ACC0. So what is ACC0? It is like AC0, polynomial size, log constant depth, but we allow all mod m gates, not only primes, composites, everything, right? So that is ACC0, ACC0. So yeah, so till about 10 years back we didn't have any such thing, but now at least we have this. We have to go all the way up to non-deterministic exponential times, right? So NP is non-deterministic polynomial time. So we have to do exponential time and non-determinism to find a language that is there but not in ACC0. So yeah, so as I said in the previous lecture, the progress of lower bounds in circuit complexity has been slow, and I don't think there have been significant breakthroughs after this result. So I think I'll conclude here. I think I have already said a good enough overview of this proof, of what we did in the previous lecture and what we did in this lecture. So I'll skip doing another summary. Thank you.